All right. So today we are going to continue with our discussion of relational algebra. So relational algebra, it would be maybe useful if on the side, maybe you have some notes about the operations, the union, the intersection, set difference, cross product, projection, select, rename, and natural join. And today we'll just be going over some more examples of this, basically. So each of these examples should hopefully elucidate certain aspects of especially how to combine these operations together. Because I won't have this screen available all the time, if you have some notes to the side that might serve you. Otherwise, if it's I will upload this table to Blackboard as well. Maybe that would make things easier for everybody. Let's see. I'll call this vocab. Okay. Okay, great. So this now should be a PDF of this should now be uploaded to Blackboard. But if you have your own notes, that is even better. Okay, so the last class and this. So the last class we went over one example of. We're getting into some more complicated queries of relational algebra. So just to sort of recap, we've discussed relations. Relations are a schema and an instance, where the schema is sort of defines the columns of a table, both the names and the types, as well as the instance is sort of the data of the table. And relational algebra is about how to query relations. And this is sort of the more interesting part of relations. Defining a relation is just defining tables, but how to query them, in particular when you have multiple different tables together, is what relational algebra does. And this is now getting very, very close to SQL queries, where there's a certain number of these operations or functions. We've discussed 8 of them. And depending on the way that you are forming a query, will use some combination most of the time of these operations. So the last class I defined up here these 4 relations. We have a person relation, frequents relation, eats relation, serves relation. And then the query that we wanted to perform was to find all restaurants frequented by at least one person under the age of 18. And there's 2 ways of doing this. And I should go ahead and say right now that for particularly when you have more complicated queries, there's multiple correct answers. So any answer that is correct is a correct answer and acceptable. In the cases that I present where it's very clear that there's multiple answers and maybe one is preferable over another, I will try to make a note of it. But that being said, just anything that is anything that's correct is correct. So yeah, if a certain approach appeals to you, just use that one. So for this query, there are 2 ways of going about it. One is using the natural join, and another is not using the natural join. For the time being, I would prefer you to try to avoid the natural join, just because it's more explicit when you avoid it, and I think it will help later to know sort of the lower level details, what's sort of happening under the hood, so to speak. When you are actually working with a system, then you can use a natural join, and that is fine. But for the time being, I would prefer you for the next examples to try to avoid it. If you're struggling with it and somehow the natural join just really resonates with you, I guess it's okay. But I'll try to have you to avoid it if possible for the time being. So to go over this example from the last class, finding all restaurants frequented by at least one person under the age of 18, we are combining these 2 relations, the person relation and the frequents relation. And each of these share the name attribute, and the way that the natural join works is it takes 2 relations, and you can be explicit and put, for example, here name underneath this bow. But here, because this is the only attribute that these 2 tables share, then I can just leave this out, and it's sort of understood that the one column that they share in common is the one that it's referring to. But I guess for now I'll make it explicit. So the natural join will take these 2 tables and it will concatenate them together, only keeping And when it concatenates them together, it does this sort of row-wise, like this. So it'll glue these two tables together to make this kind of mega table. But because here the name column appears 2 times, it will only keep one of them. Here I'm keeping this first one. And that's the schema portion of it. And for the entry portion of it, it will keep the row if the name column of the first relation, person, equals the name column of the second relation, here, frequency. And in this example, there's no overlap between the entries of the name person relation and the name frequency relation. So the result is an empty table. And everything else is kind of not so important because it's an empty table, so you'll be returning an empty relation. But the other parts of this are to first select those rows. Well, maybe I'll make this a little bit more. Let's see. If I were to add John eats at McDonald's, just to make this a little bit more interesting. Get rid of that. Yeah. Okay. So here, John Okay. So now this sort of bow tie part includes one entry, one row, because John appears in the name column in the person relation and also appears in the name column of the frequency relation. And everything else is sort of glued together in this kind of mega table. In addition to that, so this is now just this bow tie portion of it, the natural join. It so happens that including this select, so if this table were, if it had, I don't know, another entry here, Amy, who was 19 and female and also eats at McDonald's, whatever, then this select operation would have the result of eliminating those rows where the age is greater than 18. And so we would just have John remaining. And the pi refers to how to just select a particular column's entries. So the result of this whole thing then would just be McDonald's, because that is the entry under the restaurant. So first you build the table by doing a natural join. You eliminate rows with a select, and then you print the column values with a projection. Okay, so that is how this would work with a natural join. But really, this natural join, well, before I go into that, I want to talk about this example, because this is the way I would prefer you to approach things for the subsequent examples. Although I'll give both, I want to make sure, are there any questions about this before I move on? Okay. So the natural join is really just it can be replaced with three operations. That is a rename, the cross product, and adding to a select. Okay, so the cross product will glue these tables together. Oh, this. Taking the cross product part of this would result in this kind of table, where you take the person relation and the frequency relation and just kind of tack them together. Also, where there's well, they get glued together with the schema here. So this schema, name, age, gender, appears in this part of the of the schema, and then the frequency table here is where this part of the schema comes, and so you get sort of a mega table by this. As far as the entries are concerned, it's all pairings. So John, this entry gets paired with every entry in the frequency table, and Peter here also gets paired with every possible entry here. See, I think I did this earlier here. Yeah, go ahead and take that. Great. Okay, so this table now is just the cross product of these two. So John gets paired with Mary and John gets paired with Susan, or this row gets paired with each row of the frequency table. So that here are these two entries. John 16 male Mary McDonald's is this first row, and John 16 male Susan Henrys is this second row. And then the second row gets paired with every entry in the frequency table. So you have Peter 19 male paired with Mary McDonald's, Peter 19 male Mary McDonald's here, and Peter 19 male Susan Henrys, Peter 19 male Susan Henrys for this row. So this is just the cross product here. So this cross product, I'll repeat, has sort of two notions to it. First, it glues together the schemas, and then for the entries, these are all possible pairings between each entry in one table with the entries of the other table. It doesn't really matter which direction you go. You could think of this as pairing Mary, this entry, with each entry in person, and Susan, this entry, with each entry in person. The result is the same, but the number of entries here will be the size of person times the size of frequency. So here the person has 2 entries, frequency also has 2 entries, so this table has 4 entries. Okay. So this table now is just the gluing together of persons and frequency. But because we want to check now this name and this name, these columns have the same names. And so if you were to talk about a column by referring to it by its name, it would be difficult to know which column we're talking about. So after this cross product, we are going to rename this column to be something different. So now there's no ambiguity between these two rows, between this column and this column, because now they have different names. This will be called name, this will be called name2. And now when we do a select, like here on the natural join, in addition to filtering out people who are under the age of 18, we will also require that the entry in the name column equals the entry in the name2 column. So because John is not equal to Mary, this row gets deleted. Because John is not equal to Susan, this entry gets deleted, and each of these actually get deleted. So we end up with an empty table here. And then the project part is the same. So, okay. So the natural join here, this bow tie, can be reproduced using a cross product, a rename, and adding a part to the select. All right, so that's all that a natural join is it's a combination of those three. Okay.
Do you mind? I'm sorry, can you repeat the select part one more time? It's less than 18 and what?
Oh, this part?
Yeah.
Right. So for a select, the select can have you can think of a select as an if statement. And if you have multiple if statements, you can just sort of combine them together in one big if statement. So you could have this be a select where age is less than 18, and also a select where name equals name2. You could have this type of thing where you are kind of nesting these selects together, but it's a little bit cleaner to just include these in a single select statement. So you could have a select where you have condition 1 and condition 2 and condition 3, and so on and so forth, as opposed to select condition 1 with another select condition 2 and another select condition 3 on some relation. So you could sort of do one if statement followed by another if statement followed by another if statement, but it's just a little cleaner to write it in this way. So here we have while if you're using a natural join, you're just checking the age portion of it. So you want to delete the rows where if there was, I don't know, Amy, who's 19 and likes eating wherever, then this select would have the result of deleting rows where the age doesn't fit here. In addition to that, when you're not using the natural join, you also need to make sure that the name columns match. So here, this name and this name, you only want to keep those rows where the names are the same. So if you were to have another entry here, John, and he eats at McDonald's, then let's extend this. Okay. So now if I add this this entry here, John McDonald's, then John, this, oh man, sorry, it's getting really messy. Let's erase some of this. Okay, so when I add this entry here, John, so now there's 3 entries in the frequency table, then the Cartesian product pairs John with these 3 entries. So John 16 male, Mary McDonald's gets this row. Then this pairing is this row. This pairing is this row. And then Peter also gets paired with Mary, so that's this row. Peter gets paired with Susan, that's this row. And Peter gets paired with the John row in the frequency table, so that's this row. This name equals name 2 are keeping those entries where the name 1 and the name 2 are the same. So here, this row would get eliminated because of this select. Here, John does not equal Susan, so this row gets eliminated. Here, John equals John, so we keep that row. Peter, this row would get deleted. This row would also get deleted, and this row would also get deleted. So out of these, we would only keep this one row here. John 16 male, John McDonald's. So this is sort of reproducing the effect of the natural join, where you only want to keep those rows where the named entry here is equal to a named entry in another relation. So this happens, this is what's happening under, under the hood with the natural join. But here we need to make this explicit, because without this, without the name 1, name 2, then these 3 columns would all be acceptable with this age, because John here, all of these are under 16, and we don't want to output McDonald's, Henry's, and McDonald's with our project here. We only want to keep this one entry here. Ooh, sorry about that. Okay. So Sorry, I don't know who that was asking the question. Does that answer your question?
Yeah, that was me. That makes a lot of sense. Thank you.
Okay, great. Okay. All right. So these will be our running examples. Mm. Okay. So I don't really care about the entries of these tables. Yeah. Okay, so really I just care about the schemas for these questions. Um, um, all right. So here is another query that I'd like you to answer. So find the names of all females who eat either yogurt or salad or both. And reminds me of the timer. I'll give you guys like 3 minutes for this. And move this here. I need to share this. Where? Okay, so I'll give you guys 3 minutes to work on this. If you think you have an answer, you can go ahead and type it. Yes. Just like Lydia did. Thank you. Okay, great. Oh, let's see if I can stop sharing that. Close out of it. Okay. So I see. First, I'll start with. I'll just go from top down. So we have Lida, sigma, food, yogurt, and slash or. No, no such thing. You cannot do and or. I'll write it. Yeah. How can I go into this? You have to choose one, either an and or an or. Uh, goes and or salad, sigma, gender, female.
I just have a clarification question for like food. If it was both, are you saying it would like print both if you had that entry in, or would it like be like a comma? Like how would it actually print? If that makes sense.
Yeah. So the print would only be printing names. So let's see. If John, who's 16 and a male, and I don't know, Amy, who's 25, female, and if John eats yogurt and Amy eats salad, then this would print John and Amy. So that's what it would print. So
I meant like so if someone like chose yogurt and salad, like because you gave the option of someone saying both of those, like how would that show? Like if someone had both.
So if Amy also ate yogurt,
Oh, that's okay. That helped. Thank you.
then it would still only print John and Amy.
Gotcha.
Right. I'll try to share a document for this, but I think you guys should have seen this in your Foundations of Programming course, where this symbol here means or. So you have this symbol that means or, and this symbol that means and. And if this were a truth table, then 0 or 0 is a 0, 0 or 1 is a 1, 1 or 0 is a 1, and 1 and 1 is a 1. So if this were sort of a truth table, this is the they eat if A were yogurt and B were salad, then it means if they eat only salad, only yogurt, only salad, here is only yogurt, or they eat both, then to print it out. Just for comparison, if you had A and B, then only if A and B are both present, then it results in a true value. Otherwise, it's a false value. So this example is concerning this situation. Otherwise, if I discluded the or both, if this part wasn't here, then this would be an exclusive or, which is this type of table. So this is an XOR. If only one is true. All right. This is getting more into the so-called relational calculus, which I will be getting into not in this lecture, maybe next lecture. I will upload before next lecture a readout from, or a very nice document from another professor in the department who put together a nice thing for this that I like very much. So that will be extra reading for people. Okay, let me see Tushar. So he has pi, name, sigma, gender equals female. I'll go ahead and use the symbol and food equals yogurt or food equals salad. And name equals name 2. Person cross I'm guessing you want a row. Name to name 2 of eats. And that is correct. This works. So this find the names is this pi symbol. So we're only printing off the names. We want females, so that is this part. We're selecting just those rows of this mega table where the gender is equal to female. This part checks the food being yogurt or salad. And then this name equals name 2, and this rename and the cross product is like the natural join. So Tushar, that works. Let's see if Jamie has equals name 2, gender equals female, and so Jamie, that's correct as well. Danielle, yes, gender female, and food equals yogurt or food equals salad or both. Yeah, you don't need to say food equals both. That part is not necessary. Eats times rename name 2. Almost, Danielle. You're forgetting the person relation. And the rename is applied to eats. But other than that, that's pretty close. Eats times food. Yes. Except the rename is only applied to one of them. It doesn't matter which one. Eric, pie, yogurt, or salad. Yes, Eric, that looks right. You're just having more than one sigma. So the way that Eric, I think, is writing this is, let's see, food, yogurt, or salad. Yeah, so he's just adding another sigma here. So for example, gender equals female of this, and he's getting rid of one of these and kind of nesting these together. That works as well. Yeah, either way. Brian, my name. Yeah, that looks right. Okay, great. Let me go back and leave what I had before. Well, okay. Before I move on to the next example, is this one clear? Are there any questions about this? Okay. Then just for the sake of completeness, if you were to use the natural join, this would be pi name sigma gender equals female and food equals yogurt or food equals salad applied to person natural join eats. Like this. Okay. So this would be the way to do it with a natural join. You save a little bit of space, but thank you everybody for attempting it with this without the natural join. Okay. Let's go on to the next example. Yep. Okay. By the way, is 3 minutes, is that an appropriate amount of time, or was that too long for people? Because I can shorten it to 1 minute or 2 minutes or whatever you like. This next example should be about the 2 to 3. It was good. It's good time. Okay, I'll stick with it then. All right. So this next one actually might give you a little bit longer. This is a little harder. Okay. So find the name of all females who eat both salad and yogurt. Well, actually, let's see. I see that we're coming up to the end of our class now. So I will, yeah, I don't want to give people time. Yeah, I'll leave this as I guess as an example for you to work through. I'll start our next class with this, but I will say that this is maybe not necessarily so straightforward. You will have to use something else. So this requires more than a projection. Before we were just using a projection and a select. Maybe a projection and a select and a renaming and a cross product. In any case, this example, you'll need to use something else from this so-called vocabulary of relational algebra. So that will be your hint, and I'll start off the next class with this. So if you have a good idea, I'll ask if what you come up with, and I'll do that the next class. In addition, I will give some more practice problems the next class that are just going to be of this sort of the things that we've already done today, but just different iterations of it. Nothing that is harder than that. So each of these examples are kind of increasing in difficulty. So that is it. If you have questions about the homework, you can email me or ask them on Blackboard, and I hope you have a very good weekend. I'll stick around for a few minutes if anybody has other questions about today's lecture or the homework. Otherwise, have a good weekend. Toyin. Yes. This would use uh, the intersection. Correct. That is the other part of the vocabulary that you would use. That the notation is this. Yeah, it's called a cap. Uh, okay. Yeah, Alejandro, do you want to unmute your mic? I can open up the homework too. You can ask.
Hello.
Yes.
Okay, so yeah, for number two, I'm still kind of confused a little bit.
Mm-hmm.
What I have is an employee can purchase exactly one policy covering zero, one, or many dependents. Also, each dependent can be a beneficiary of exactly one policy purchased by exactly one employee. I don't know if that's the best way I can like kind of interpret what the R diagram is trying to say. Like I'm paying attention to the black arrows, and those mean at most one. So I just think that employees they could have like different dependents under one policy. Like each employee has the opportunity to have like to purchase a policy that has many dependents. Like let's say 2, 3 people are under age 18. So yeah,
Okay.
that's my interpretation of it.
Can you? Let me see if I can stop this recording.